各位老师、各位同学哈，欢迎大家来到今天早上这个 seminar。我们今天很高兴请到 NASA 蔡希奇博士为我们来做一个演讲。那蔡博士是1977年毕业于台大大气系，后来在1986年在阿拉斯加拿到博士学位。那后来到这个 NASA 来服务，目前在那边工作。那我们今天很高兴请到他来为我们做一个演讲。我想我们先很热烈的掌声欢迎一下蔡博士。You can speak more English if you want.
We have from BPM students, so we have an international.
Just one intervention. So you are absolutely so we vote you are. Okay, anyway.
Which I think the International Institute. Anyway, that's the policy.
Okay, anyway, 我还是觉得讲中比较，看理比较顺哈。刚刚到那个林校长室跟林校长他们讲，这次来最主要有2个目的啊，其中一个目的呢就是有关于这个下面5年啊，我们是在 push 当 international monsoon year 啊，那 monsoon year 呢对 monsoon 对这个Asian area 是非常 important 啊，那所以这个呢是 one of the monsoon regions that related to， 所以这个 topic 呢。是比较对我来讲比较新哦，但是 I'm taking the challenge, so okay, if you want to ask me question, that's fine. 所以这个是我去年9月去这个非洲做的一个实验哦。那这个呢就是 something related to 这个 Saharan dust how it impact on this tropical cyclogenesis。那当然，这个在台湾这个台风啊是很重要的一个 phenomena 哦。那基本上很多物理现象哦的背景的那个物理原则大概都有类似性。Spectral 那个characteristic to do some of the study on how the property of the dust can be applied to your model or your research. Okay, so everything is related to NAMMA. Okay. 这个是非洲的实验，这一张图呢是非常有名，因为这是2000年2月29号，就是 Terra launch 完了以后 ，after first flight， 你知道卫星打上去以后啊，要有将近1-2个月的那个 outgas 完了以后呢，就真的能够 operate， 但是一 operate 呢，马上 catch 到这个非常新的一个 phenomena， 所以希望你。Take a close look at this 这个Saharan dust outbreak 出来以后，有2个很重要一个你看这一条线，这个是 associated with 那个 African 这个 mid-level easterly jet， 这个 easterly jet 呢是 control 这 cyclogenesis 的一个很重要的因素因为基本上这是 related to 那个区域另外上面的这个 anticyclone 的那个 main 的那个 outbreak 在上面这个是1999年第一次提出来的这个 Saharan area 的那个 concept， 所以你可以知道说，所有的 dust storm 的 outbreak 有不同的dynamics 如果说在 Africa 呢这边，或者在 Arabian 那个 peninsula 基本上是 related to 这个subtropical heat 的那个 sunshine 的那个，所以 generate 自己的那个 heat load 所以你可以知道这个升温上来但是如果说在 Asian dust outbreak 它不大一样，它是 related to 那个cold air outbreak 或者是这个 Bantu activity， 或者这个 Mongolia 的那个 cyclonic 的那个 depression， 所以这2个是不同的 mechanic， 但是它基本上 carry 出来的 dust 呢，它的 impact on 这整个 downwind 的情形是有一些历史physical 的那个类似性所以你可以看得出来这个 model 里面这个还没有到这么 sophisticated 的那个 video 是能够提出来的。这一条就是 easterly jet， 这个是 anticyclonic 的 activity，major dust here 所以我把这个稍微介绍一下以后李老师都知道我很喜欢臭屁， 很多人都认为说，这个 experiments 跟这个 model 啊不能办法沟通，因为每个人的 perspective 不一样。当你去做实验的时候，很多方面的人认为说，我们去享受这个feel 很舒服。来，我给你看，当初我在这边1个月啊，你天天所看到的，你的那个 life 啊 ，supporting your life 这2个东西，对不对 ？fundamental， 一个是什么？一个是 air， 一个是 water。这个 California 啊，在他们的眼光中是 Africa 的 Hawaii。California 就跟 Hawaii 一样，它是这个岛一直在生长哈。在 California 现在有10个岛，7个岛可以住人。OK， 但是这个我们这个 experiment 在这个 salt 上面哈，这个 salt 呢，你如果看这样我写的那个 footnote 啊 ，salt 呢就是盐呐 ，Portuguese SAL 就是 salt。OK， 所以你很清楚说这个岛唯一出来的是什么？是 salt。所以你如果在这边待1个月啊，I think you're gonna go crazy. Nothing but salt. OK， alright。那第二个 life support 的 important 是什么？是 air 啊，是那个 water。所以这个 water 呢，全部是从 Portuguese 呢 bottle 啊那些送过来的。So this is how experiments live under this kind of condition. OK， 所以这个是所以不要以为说个人的背上的那个包袱啊比较轻。Actually, the experiments, they have to risk their life to take the first hand there. Just like in the model, you have to sit in the computer room, right? You have to crank your brain to get the physics correct, right? So this is something. So 以后我们不应该互相有。Okay, so what's the rationale for this talk? 这个是 Saharan area. OK， 现在我想要告诉你的就是2个东西 ，Saharan area 跟这个 tropical Cyclogenesis
有3个从汉城，国立大学，要英文讲，你们有没有问题？没有问题。啊，还有国际学生，
继续讲，因为我听不懂。
他不会吹水啊 ，OK？ Okay, anyway, okay, and now I'm switching to English, all right? So what you want to really understand is this Saharan area and related to how it's tropical cyclogenesis. Okay? This is one of the cases. We were there for a month, but anyway, this is first case. When you see that, you know, this is ITCG related to African East wave. Okay, so you see that coming up. But this day, this cluster didn't form a cyclone. Okay, but if you look at closely in here, that's dust outbreak. Okay. Yes, this is all the dust, okay, coming up here. And this is the sun grain, so forget about it, that's different phenomena. Okay? So, what is the definition of Saharan area? Okay, this is mainly is the hot and dry dust laden will meet there up to 500 million, 500 million dust. Okay? And the oil is associated with African wave. Okay? Then, for the back, the past research, what is that? We don't understand from radiation. You know, the Saharan area, this SAL, is stabilized low altitude. I have another chart to tell you. I just want to give you this very quick background. Okay, let's leave this until the next one. Okay, but then it's also regulated the strength and structure of mid-level easterly jet. That's the one I previously showed you that more this big jet. Okay, but the impact remains inconclusive. We haven't got a really definite which one, related to which one. Okay? This is another day. We formed the cyclone, Saharan. Okay? This one for the 206 is one of the big one. Okay? And then if you look at closely, there's no air dust. Okay? So this will give you a rationale. You know, dust may be related to something about this Cyclogenesis. Okay? So this is how we start doing that. And this is the chart I want you to take home. If you think you stay here for an hour, this is the chart I want you to take home. So what we're interested is this side, how is extensive aerosol related to this side, the current water cycle. Okay? I think that water is one of the major elements for human being survival. And then NASA's next 10 years, immediately strategy plan said, water cycle, fresh water redistribution is going to be our major challenge for the next 10 years. So this is the topic that we really want to talk about. Okay. So how these two related? What I do is I use the two different processes to describe it here from this way out. The one I call macro scale process, basically related to the direct effect, aerosol direct effect. When the aerosol big area come out, it cools the surface by blocking the sunlight. Okay. And then the second one, we know aerosol is not all pure, always has some absorptive stuff in there. So when you have that, it's going to cause increase the stability because it absorbs the sunlight. When the sunlight is absorbed there, it stays heat there, and then it means that it's warmer in the air. Okay. So for this one, I will give you one example called dimming effect. You know, remember recently everybody talked about the aerosol cause the decrease of sunshine, sunlight, you know, and then some all those scans running out all the GCM and come up the global dimming effect, right? So I'll give you another one chat later. Talk about it. The second one called micro scale processes. Now macro means a bigger, right? Micro means very fine, right? So this one, the scale probably tens of 4, 5 meters, the scale. This one, micro, tens of 6. Okay, so this is very small. So it's related to how this tiny aerosol affecting the cloud droplets. Okay, it's called nuclei. Okay, so the first one called indirect effect. First kind. Well, they are too very sophisticated. But anyway, don't believe that one. Just get the sense of that's enough. So, Toomey effect is the general term for this one. Toomey, this is very famous cloud physicist. He originated from Australia in the 60s, 70s, when the cloud physics boom time. He's the first one pointing out this how aerosol, the nuclei, cloud condensation nuclei, affecting the cloud formation. So in here I said widen or darken the clouds. When you go to the larger scale, it's very straightforward, clear, okay? But when you go to micro scale, then it could be have a different effect because this is so sophisticated in the processes or the mechanism, okay? So when you look at that time, he's looking at the marine boundary layer cloud from the Australia. So the marine boundary layer cloud mainly is now pristine air, right? So the cloud droplet is large and a whole bunch of water vapor. In that case, when they, the early days when you have the sugar cane, after you harvest it, you burn it. Okay, the same thing in Hawaii, the same thing in Taiwan, the southern part of the island. When after you have the harvest, the agricultural waste, you already burn it. When you burn it, that produces a tiny particle. And that particle, if you get into the marine boundary layer cloud, because it has a lot of water vapor and the droplet is large, so you form more the cloud droplet, so it's smaller. Okay, so in that case, when you have smaller droplets that have a more backscatter, so that's lighten your cloud. But then, if this aerosol come into the continental cloud, the continental cloud is already a huge, big one, right? And then has many, many nuclei already. So that won't trigger the activation of the nucleation. Then that small particle, it gets into the cloud, become between the cloud droplet. So that will darken the cloud. So this is somehow two competing effects, depends on your environment. Okay? All right? Okay. The next one, this is talking about boundary layer cloud, the water cloud. But then for Saharan dust or Asian dust, sometimes they go very high. And then the ice particle is an ice nuclei, very nice ice nuclei. When the ice nuclei get into there, the saturation vapor pressure for ice is quite smaller than the water, which means they will go up at the expenses of evaporate the water droplet. So the ice particle will go bigger. And then when it goes bigger, you fall down, right? And fall down, that's one of the mechanisms to increase the rainfall. So in here, you have to take home. This is pretty subtle difference in here. From the micro scale and micro scale, the mechanics, the physics behind is quite different. But what you have to do is quite careful on all these effects, right? So all these two will alter the heating gradient. See, when you have a dimming effect, when you have the cooling effect, you change the heating gradient between these two environments, right? And then it will change the convection and change the saturation. So this is how it affecting this water cycle, right? But this is not one-way street. When you have this direction affecting water cycle, then it will trigger the feedback processes. Okay, so the upper part of the feedback process is kind of like a wet removal process. So you see that the cloud, water, vapor dynamics, all this stuff is going to feed back to this extensive aerosol, take away something. Okay, and down here, this feedback process is kind of dry type, dry removal processes. Okay, so that will change the transport, deposition, and chemistry, and this aerosol-aerosol interaction. Okay, all the aerosol has their different type of chemical property, so they interact each other. And then when they interact each other, they will change their property. Okay, so this part is the feedback, and I'll give you one of the elevated heat pump hypothesis or effect. I'll show you for the next three. So this is the view graph I would like you to take home. If you think 1 hour in here, that's probably the most. All right, let's go some fundamental basic physics for you. The macro scale processes. If there's no aerosol for the ordinary environment, this is how it works. Now sunlight comes in, hit the surface, right? Involve the surface, right? Produce the convection. Okay? This is very schematic. So this is how it forms the clouds and then all the convection, right? Then the other side, if we artificially introduce this aerosol in here, either absorption or non-absorption, what you do, the first thing is blocking out the sunlight. So basically, you would introduce a little cooler surface. But then if you have absorption in here, you will absorb the heat, so the air will become warmer. And then that stabilizes, so it breaks down this convection. So it won't produce more cloud or more precipitation. So this is what the dimming effect. Okay, this is the background of dimming effect. The next one, what is the? Let's go. What's missing here? Oh, yeah, there's another picture here. I don't know why it didn't come. Okay, this is one of the example that how the aerosol will cause the cloud brighter and longer lifetime. Okay, this is one of the satellite observation by Trim. Okay, and over there has this is the imager and it has a microwave diameter. From the imager, what you see here, this is in the southern part of Australia. Okay, so this is the low-level water cloud. What you see in here is three patches. This one, number 1 and number 3. The satellite retriever will tell you from here, the particle is large. Larger than the precipitation spatial particle size. So it will rain. So this too is raining. But this one is not raining. Because look at that, it's a particle small. Okay? And then if I look at the microwave diameter, you see that this particle is moving up and then this is, okay? The total water supply there is about the same. But this part did not have this preset. Okay? And this part you can see that it's darker, not brighter, and this color scheme is a little bit different. Okay? And if you see the white stuff, this means that it's preset. Okay? So this is one of the mechanisms caused by suppression of the rainfall because the pollution coming in this way. So underneath as the aerosol comes in, so masked by the cloud. Okay. So this is one of the examples showing why the micro scale is really complicated. Right? Then another one, the last one, about the feedback. This is you see that from the this is very simple, conceptually you can understand very easily. Next one, make it more and more complicated. I didn't have the picture here. This one is the LiDAR showing in the Saharan air outbreak in 2002 when the dust particle getting very high into the cirrus cloud to create more and more bigger and bigger the ice crystal. So that part will show you the other direction that it will increase the precision. Okay. Anyway, I don't know why it didn't show up. The last one is getting even more complicated. This is called the recently now, and we study. Actually, this is the one that when I talked to your president about the next 2-3 years we want to do is related to this Himalayas and Tibet. Okay, we come up with elevated heat pump, in fact, and this elevator is built to orographic. Okay, because they have the this is Genji, Gangetic Basin, and then this is the Himalayas, and then this is the Tibet. But if you have a different mechanism, like air leak, when the aerosol was lifting up, okay, it will cause the same or similar phenomena about this dynamics. Okay, okay. So what we did is, this is the usual Indian monsoon. Okay. So when you see that, it rain everything all regularly, but then the other scenario is when, Indo-Gangetic, this basin hosted about 10% of the human population there. About 60 million people live in this Gangetic plain. Last year I went there, and then year before that I went there too. I have a whole bunch of pictures. But anyway, what you see that is really dirty. I think we have the native Indian, right? You probably understand it. Okay. So what you see that this aerosol comes in and pile up against the Himalayas. Okay. And then you change the previous one, the thinning effect. You change the cooling, and then you change heating in here. So basically, you create another secondary circulation there. And then when you change that, you change all the heat preset. Okay. So we come up with this postulate, we change the Indian monsoon, okay, become earlier. Then it triggers when you move, the pattern moves to the north, and then it intensifies too, okay. And then this is what the paper, the first one talked about this mechanics. The second one we just submitted, talk about how this impact, okay. So this is the 3 pictures supporting that. So now we come back to the main subject of this talk. This is the one I think debating quite a lot now in U.S. In 2005 is most active hurricane year in U.S. The eastern western Atlantic. Okay. So last year they forecast based on the dynamics and then environment. They think 2006, if you see here, above normal. When it's above normal means it probably 10 to 28 tropical cyclone, right? Tropical storms. Okay. But actually, last year, 2006, it only had 9. And then this is a very big blow up for the NOAA. So this is the subject that I want to talk about today, all right? So very quick. So in here, what we put in is, there's so many parameters here. How we try to look at this relationship, okay? So in this chart, what we're trying to show you is, we look at the dust, sea surface temperature, and the storm. The tropical cyclogenesis, okay? And then this is the 3 months average. Okay, so this is the storm season, all right? So that's what I said previously. 2005, this is what happened. Hurricane, tropical storm, and tropical depression, and last stuff. Totally about 27. So last year they forecast it should be that much, but it's only occurred that. So this is really a big difference from what the forecast and then the actual occurred. So what we showed is 2 different things. One is the sea surface temperature, and then the other one dust loading. In dust loading here, this is universe. Basically, it's aerosol index. Okay, so you can easily translate. That means some kind of how much dust is there. So what you see here, this is 2005. We have so many. This is dust storm track. There's so many. Okay. And remember when I get into Taida, the first year, 大概 101, right? We talk about the magic number. Okay. What is a tropical storm or typhoon? The sea surface temperature has to be greater than 20 or 29 Celsius, right? So this is the curve. You probably cannot see that well. This is the contour curve. How big is that sea surface temperature area in 205? And then this is 206. A big stream on that. Okay? So in this one, you only have 4 or 5 on a total, I think, different colors indicate different strengths of the hurricane. Okay? So it's about 5 of hurricane here and 4 of tropical storm. Related to this, when you look at the dust loading, 205, this is the contour of the dust loading. Okay? The 206 cover larger area than this, and then stronger here. Okay? So in here, I didn't tell you anything. I just showed the fact. This is what I observed from here. Next one, people always say, wow, dust storm oil related El Nino, right? Okay, then let's put in on the table how it works. So this is the El Nino, sea surface temperature, and dust relationship. The same thing here. This one shows is the sea surface temperature anomaly. Okay? Anomaly means for these 20 years, okay, you have come up some kind of norm, okay? And then we also pick up what's the El Nino year. You take a difference. Okay, so what you see here, this is the El Nino, right? Everybody knows this. Okay, this is a feature of El Nino. And then the rest of the sea surface temperature distributed like this. And we know 206 is kind of El Nino year too. All right? So we take it, wow, let's look at what's different between 206 and 205. So when you take a difference of that one, yeah, we do see the El Nino signal here. But why you see the major difference here? Look at this. This is negative, okay? It's about colder, like 1.2, 1.5 degrees colder than the previous year. Okay? But if you look at this El Nino sea surface anomaly, this area is still positive, still warm. Okay? But then you can see that quite different pattern in here. And the same thing here and there, it's all the opposite of it. Okay? But then when you look at the dust loading, consistent. This part is all positive dust loading. More dust in this area compared to this El Nino dust, anomaly. Okay? So you get a picture now. So this is one of the supporting. Then let's go one step into how it's really related. Okay? So this is one of people submitted by Lau et al. What they're looking at the past 20-some years. Okay. This picture is what we said baseline. We have no El Nino year, and we have way less dust in there. Then what you see here, this is the tropical cyclogenesis phase. Okay. This one is the normal cyclone phase. Okay, so you can see that probably somewhere around, how many 1 day per 3 months, the average. Okay, it's average. So this is quite significant. Okay? But then once that we put in, if I have the year has more dust, what happened? See, this is negative now, and then it squeezed all the occurring in this region. Okay, the dust more and the Cyclogenesis more in this area. But then, if I turn around, I have a more El Nino year, okay, with the less dust. Then what you see, this is almost image relationship. All this is negative. But then the dust occurring test is shift this way. And then when you have, yes, I have El Nino year and also more dust, everything is negative. Okay? Which means it tells you something, yes, El Nino is one factor, but probably dust is another initial triggering parameter. Look at it, it's quite different from that. Okay? So this is the way that gives us, actually I will tell you the result. Okay? This is the result. But anyway, let me tell you how we're going to proceed and do this kind of research. Right? So, August to September 15, 1 month. NASA launched this African Mission multidisciplinary analysis. Actually, AMA is the European supported more than 10 years activity in Africa. But NASA was pressed, pretty hard by the taxpayer. 2005, Katrina, okay, for example, Katrina is the one really caused a big damage to U.S. Okay, so NASA was present. Why NASA didn't have any action? So then, at last minute, we were told to go to participate. So this is the background about the NAMMA, right? We're taking for the difference between these 2 years, the 2 period year. You know that this is the deficit of the precipitation over land. Recently, that I think you guys have been seeing that the inconvenience truth and inconvenience truth filmed by Al Gore. Recently, that's one very interesting picture about Lake Chad. Now, in the 60s, for the 60s to the 1980s, the Lake Chad is the biggest lake in the African continent. But after 30 years, the entire lake disappeared. No more water. Okay? So you can see that this recently has another paper comes out showing the most dust coming to Caribbean, this area, more than about 70% of the dust coming from that lake. Because that lake dry out, the lake sediment will become easy to lose and then break it. And then when you have the dust coming in and the strong wind comes in, you trigger all the dust coming. Okay? So you can see that this is the background behind. So that's why we conduct this experiment. Okay? So what we do is we have this satellite. We have the aircraft. We have a radar. We have my smart commit. I'll tell you this later part. So this is all the player in here. So fitting to the entire concept. This is another chart that I really want you to bring home. I make this chart because you have three or four components. Everyone is doing their own job, but historically there are very little communication. So people like us working on the satellite, we will stay in the computer room looking at the satellite, all kind of very nice. Okay? But the satellite will provide you snapshot of global data, but they don't give you the temporal, which is only 2 times. And then you have a GMS maybe every hour, but GMS never has the enough channel for you to play around. So, and then the ground base in this side, you have a temporal resolution. You sit there, the continuous taking, but you only have a few points. Okay, so that's why you have a different characteristic of data. And then the same thing in here, the modern world, you provide all this stuff, you can do it in your simulation, but how good is your physics then? Okay. So one way to do it together is using field campaign. This is the reason philosophy that we put together. When you have a field campaign, you simultaneously bring all this into the picture. Okay. So let me quickly, because I only have less than 10 minutes. All right. So this is one of the dust storm, dust storm outbreak. So you want to assessing this impact of the aerosol, you require understand all this property of the aerosol. If you come here, at least you have 7 dimensions. And this is very complicated. Now you have to understand individual refract index, what kind of species, absorbing, non-absorbing, as SO2 or CO2 or whatever. Okay? Then, not only that, you have to put it to understand how the radiation transfer will work. So here you have another 7 dimensions here also. The 7 dimensions you also can put into the fundamental element. You have a spectral, you have a spatial, you have angular, you have temporal. The Taiwanese said when you go to the market, what you want to do is you want to show the whole jack, right? In NASA, what we call is cheaper, faster, and better. Okay? But it never happened. It always failed. You wanted everything. The same thing in here. Remote sensing, you never have four of them all together. Okay. So like I think Liu Laoshi, he specialized in GMS. GMS gives you the temporal and the spatial, but never give you spectral. Okay. Then recently, like the spot or the polar optic and the Rockset 2, you have that imager. You have a spectral, but you don't have a temporal. You have a spatial and spectral. You also can get two of non-functional. So this is what the technology still haven't catch up yet. But in this case, what you want to do is you want to pick up the most effective way for you to do your research. So, okay, let me quickly. Historically, this is how aerosol is retrieved from the satellite. In the early, what you can get is only over the ocean because you only have two spectra. And then those two spectra is chosen to do the meteorological, like a cyclone or clouds. You never choose it for aerosol. Okay. Then now, recently, we have a better one. This is probably most sophisticated facility in the space called model. But look at this. The major part missing is the feather because it's so bright. Okay. So recently, what we have done, this is the Lin Laoshi, the classmate. She's the one has innovative thinking. So come on this. So this is quite a simple concept. Okay. This is a spectrometer called GOMI. The global auto mapping is a spectrometer in space from European. When you measure, this is the outgoing radiance at the top. But in here, what it is, we know that if the retrieving aerosol from the on Earth, there's two compaction factors. You want the surface darker. The darker the better. Okay? But you also want the signal stronger is the better. So when you look at the UV part, this part, this is the molecule already scattered. Okay. I'm not going to go through the equation, but mainly what it shows is inverse proportional to the spectrum power of 4. Okay. Which means that the smaller, the shorter wavelength, you have more contribution from the ray. Okay. So, but this part, the surface is so dark. This is your idea, all right? But then when you come to this time, idea, I have two different curves. This is after retrieval, removing the radio, okay? This black curve shows the Saharan, okay? This light brown color, this is the phobia, okay? At the surface, that's nice instrument too. What you see, the difference major here is when you look at the picture, right? In the Saharan dust outbreak, most of it is a brown color. Okay. But then when you go to the Chinese dust outbreak, it's more yellow. The major difference from this spectral difference here. But what I want to tell you is, yes, this is the better way of doing the retrieval, but the contribution is so slow, so small. So what is the optimum? When you do this, the optimum is here. Okay, it's about like 410 to 440. So this is how we come up with the name deep blue. This is the most successful algorithm now to do this task retrieval. Okay, so what's the difference? I want to run it quickly for you. This is the case for Asian dust outbreak from Takamatan. All right, and this is the current models. Okay, but now this is the one that after we put into the deep blue, basically fill up all this gap, the desert area. If you don't know anything about the source, how are you going to do monitoring or do this research? Okay, so this is the fundamental improvement on this. So I want to go pretty quick. And then the other thing is, this is the one you want to really pick. One of the important parameters called single scan albedo. That's a ratio of the aerosol, how much they're going to absorb, how much they're going to scatter. So if this guy goes to very close to 1, that means it's only pure scatter. Okay. If you go the other way, when you say that this kind of movement, this is already high absorption. Okay. So when you look at here, Now, the dust outbreak triggered two different sources. One is Takamaka here, the other one is Gobi here. So this area coming from Gobi is really absorbing. Okay? So the Takamaka is less absorbing. That this caused a lot of difficulty for the dynamics, how much energy will be dumped into the mark. Okay? So this is the important, and I cannot create this movie. Before you guys come in, we already spend our time trying to, using the PC page. But if I can create the movie, that will show you very nicely how, for the past 2 months in August and September, how this dust outbreak will show you how big is the area and how consistent that. Okay, so I cannot create. And this is related to that for the retrieval. And then actually what we do at the end, because previous 2 weeks are showing you is near real time. When we are in the field, we immediately receive instead of broadcast, we immediately put into the model, immediately produce that to help or to guide the experiment, how we go. Okay? But this is the afterwards we put together. So you can see that the movie, still I cannot show it. What we do is, this is for Asia, Takamaka is here. And then this is related to the COVID outbreak, the frontal system. And then the previous one, if you look at this, this is all related to the heat load coming from, okay? So it's quite different. But anyway, I run out of time, so quickly we want to show you. So going through that, what you do is you put into the with this model, and you find out, this is the clear sky, this is clear sky. The major difference is here. This is what average, spectral average absorption ratios, okay? This is over the ocean, this is over the desert, okay? It's only a very small difference, okay? 8 watts per meter squared. But if you remember that, in previously the Darwin CO2, about 3 to 4 watts. That's Darwin CO2. That will cost you that only 3 to 4 watts. If the solar constant change 1% or 2%, is about 2 to 3 watts per meter squared. So that's why even this is a small number. I'm telling you, this is a big factor. Okay? This heat being absorbed or dumped into the Earth's element system is really huge. So this is the one that I'm going to skip it. This is the one that what you want to do is, how are we going to do? I'm going to find it. Let me quickly finish about this one. Okay? So how we can do on the surface to provide you a very accurate number of it. So this is the one that in the past I built 2 trailers. And then I think that Lin has a very similar capability. Okay. In the first week, what I try to acknowledge is, recently everybody was accusing the U.S., why cost the Iraq war. Okay. It's about $1 billion per week that U.S. cost. Okay. So what I do is I try to, doing the civilians contribution. What I'm trying to do, I tell there's an Air Force quadrant. I say, hey, I need to go to the South Island, Cape Verde, but I don't have money. Can you contribute it? So they contribute 2 round trips. So you can see that these 2 trailers, entire trailer was in the aircraft. Okay, this is the scale. This is big aircraft, and then this is the cooperative executive aircraft. You can put 2 or 3. You take the wing off. You can put it in there. So what I do then, I went to the Air Force Reserve. I thought, hey, let's do something useful. So I briefed them how we're going to deal with this project. So in the end, they're very excited. I said, well, if you can contribute to 5 hours, send me there. It's an 8-hour one way. So it comes up just airfare cost is about 350K, equivalent to about a mini 1,000 台币. So Air Force contributed that for me for free. So what I do is I show them, and then last day we went September 2nd. We arrived there early morning 5:15. We pour out the first one. Well, I'm supposed to, but I have to sit in the headquarters to communicate all my crew and their crew. So I was really weak. I really want to go with them. This is the once of your lifetime in the experience, your life experience. So after the, 1 hour, we pour the second one out, and then we power up about 3:30, and then about 5 hours later, we start to catch. And very luckily, that was the day when we arrived. If you look at that one, it's so bright. It means there's no blue sky. That means there's a lot of aerosol. That's why it's scattered all the time. So you see that it's white sky. Okay, that's the one we caught it immediately that day. Okay, so quickly show you. This is my trailer. Okay, I have about 33 instruments here. Everyone works, you know. And then flying the C5, the cockpit, the cargo area is about minus 40 or 50 Celsius because there's no insulation. And my crew was sitting in the cockpit, you know, it's a little bit small, but you know, okay. So that environment is really harsh. And then this is one inside. So this is the micropulse lidar. I think Professor Lin has one in here too. Okay. And then this is another interferometer. Very nice, many homemade. Okay. And then this one called the commit. Basically, this is the one that really want to answer what kind of stuff coming to, you know, in the air. Okay. So last year, I think Carl Wang was launching this one, right? So now this is the one we collaborate with the Chinese academic science. We provide the idea how to make a new compact instrument to put into the balloon. Balloon is very important in the sense that you can control push button going up, push button going down, continuous going up and down. So one of the instruments what we try to do is to measure particle size. So this is important for body profile. Okay, but we're still going on here. And this is another one that the homemade instrument, you know, for remote sensing of the dynamics. One of the important is what is your skin temperature? You know, ultimately that energy has to be dumped back to the space, and how you going to characterize that? And most difficult is how you can measure that skin temperature. So this is one of the we try to do. But anyway, this inside the trailer. This is what we do. Okay, everything is military style. Now you look at the bottom here. We have that for suspension. Okay, this is how we do in daily life in field. Okay, but for Professor Linza in Linza, you don't have to consider it. But anyway, I need to come up very quickly. Forget about that. We lost some minutes to begin with anyway. So this is what my goal, and then this is what we do. You know, how good is this? I think President Lee liked this physics. This is really something that the spectrometer, how you see the different. That's why I call partial lambda. You know, the spectral shift of the due to different. You know, you have a bar storm, you have positive spectral shift. But then in this part, you have the other way around when you have a serious cloud. So this is something that really intriguing, that the new stuff. Okay, so this is how we do. And this is another part I want to show you. Why we spend time and energy on surface? Because you know this tropospheric aerosol always originates, you know, the activity near the surface. Okay, so for example, I always aerosol, okay? But if you sit on the surface, you can measure the chemical, physical, and then optical particles. It's measurable. Okay? So this is one reason the surface is important. Surface measurement is important. And, but all this stuff will evolve in the planetary boundary. Okay? It goes through all this diffusion, mixing, transport, and all these processes. But now this is all programmable. Like Professor Chen and all the Professor Sun. Now, this is all your modeling. All the physics described very well. So if you have this, you have that, you put it into, if you know all the, you know the process and describe what's right, then, you know, this tropospheric aerosol will signify the role in the free troposphere, because that's how you get into this affecting global okay? So how is that heating, cooling, the microstructure effect, all this stuff. But you know, we have a satellite, we have a surface aircraft all put together. Then we can answer the question. So this is why back to that triangle. You know, you obviously have to work together. Yeah. And then ask you that this is what how we're going to do it. It's very interesting when you have a dust, when you see so what the filter looks like, you know, and how the characteristic is in here. Okay. That's the last one. That's nothing either. Okay. So this is the summary that basically, NAMMA activity will shift many less for this relating to this Saharan area okay? And we do have a lot of comprehensive information now in the source and the transport, okay? So if you put all these things together, now you can put now understanding what's going on. And then this fresh water distribution is really the most important problem that we can face, okay? So that's why I'm coming here to ask him this interdisciplinary and international collaboration. So all the data we have is on the web. It's free. Okay. So anyone who want to collaborate with us will welcome. So this is my ending one. Ending figure. This is how we put together. You see that from the satellite. You see that from the surface. And then you can coordinate it very well, and then you look at the dynamics, and you can trace where the source and how it comes in, So now you have a bit better way to describe the entire picture. So I conclude here. Thank you. Sorry, I always take a little bit longer time, but not too bad, only 50 minutes.
Okay, because Chairman Liao has something to do, so thank you very much for Professor Tsai's very wonderful presentations. So my feeling is, wow, quite amazing. So please have your questions to Professor Tsai.
We have to school the president because he always asks very difficult physics problems.
Well, it's kind of a chicken and egg problem.
Yeah.
I mean, the small scale aerosol operate, and the large scale activities like the El Nino. I mean, the interaction between walls is kind of chicken and egg.
You missed the first part. What I said is, what we're trying to do is bring up all the factors there. This kind of aerosol, of course, you have to look into it's an initial trigger. When it started, immediately the dynamics will take over. Okay? But when it's triggered, that's the time you want to understand. So that's why, remember the three different type of facts that I put in. Look at the sea surface temperature, look at the annual, look at the dust loading, look at all stuff. I'm not telling you this is the truth, but I'm telling you this is all the fact. Okay? We have been observing this, we have been analyzed this, and then which one, and when you're going to play it. That's the time we have invited the innovative scientists to come up.
For the model, the Professor Sun, you have any comment?
He's going to kill me. He's going to kill me.
I would like to ask, how come the 2005? You have some kind of cool surface, and 2006, you have a warm surface over object, right?
No. 205, the surface is warm. Warm. It's warm.
No. Right now, it's okay. You have a more dust on 206.
Okay, right.
You have a warm surface, one land surface, okay? So right now, land over the land, okay?
Yeah.
So the 2005, you have a cool surface, cool land
surface,
right?
Yeah.
So actually, the cause of that, what's the cause of that? Okay. So right now is that you always emphasize, that you have more dust or less dust. But
sure, I did my job.
From the meteorology, right?
Yeah.
So that's the cause or the consequence.
Well, I cannot answer because this is not my part of the strength, okay, the dynamics, okay. But what I'm saying is that in here, what you see is, for cyclogenesis, the trigger part is the sea surface temperature, right? And of course, the land maybe warmer or cooler. It depends on the previous precipitation, right, over the area. But that is something beyond the scope. But what I'm saying is that
that's not your job.
That's your job. But what I'm saying is that now look at that. The the 205 and 206, the dust outbreak at the land. It's different. But why it's different? It could be related to the precipitation before. And how this precipitation was caused that? That's related to the dynamics, right? Nothing to do with it. But I'm taking care of after that, the outbreak. Then we look into what after this. So after that, you see that the sea surface temperature really changed. 1.2, 1.3 degrees, that's pretty large, right?
Yeah, I think what Professor Tsai said today is he gave us some hint on the difference. You compare 2006 with 2005, they see the difference in the dust loading and also see the difference from the sea surface temperature.
Yeah.
So of course they are not, I think we still need to do more work to come up with some better idea to see what's the difference. What makes the typhoon prediction or hurricane prediction in 2006?
Yeah, where they fail, you know.
Yeah,
there must be some physical processes that is quite right or missing in your predicting model, whatever.
I think
so you mean that
I open the can of worms.
the failing of the prediction is just due to the model does not include the effect of aerosol in the model dynamics?
Could be. You know, this is why we went to the Tibet, we went to India, that invite them to come in to talk. Because the monsoon community, they always say, forget about the aerosol. It's not going to be important. Forget about it. But then if you forget about it, you tell me why some phenomena you cannot explain. You know, we have to open mind. We have to open mind. Everything could be possible. Let's discuss. This is the purpose. Okay. You know, I think that we should not afraid of controversial issues. What we should avoid of, we are not open-minded to discuss.
Yes, so
look like the dust has a separation effect.
No, I didn't say that.
Well, that's what you present.
If I say that, I'm out of job. Okay, come on. We still need the grant. This is grant.
On your presentation, compared to
Yeah, it looks like.
from 6, right?
It looks like, yeah.
So, anyway, since you mentioned there's some variety, like buffering effect, you try to give it two possibilities, but in the end, you're more like a.
No, actually, that's another hint that at the beginning I said that mid-level is the jet. That jet is the strength, and then the position that will really control that cyclogenesis. But this jet, where located and how strong that is also related to the Saharan air layer, the energy release. But this part, I have no observation. I have nothing, so I didn't say it. I just presented this is one of observation. And then it requires, because as I said, you know, look at that triangle. Our observation always a patch, you know, from satellite. You don't have a temporal resolution. From the surface or aircraft, even worse, you don't have a spatial resolution. So we only really rely on the model to bring this together. Modeling is an integrator. Okay, so this is really needed. But you know, in the past, you know, not much of the communication between the experimenters and then the model. But I hope that they're going to change now. You know.
So do you have some observation data for microphysics?
What?
For microphysics in NAMMA?
Yes, we do. Yeah, but it's only on the one side, the saw, and then also some of them from the aircraft. Yeah, it's going to be released publicly.
So you also have like a drop sound?
Yes. It's actually all in the web page now. It hasn't opened to public yet because it's still in 6 months period. All the PI is still working on it to fine tune it. Okay.
Yeah, for the 2-minute effect you mentioned.
Next time, come on.
You mentioned for aerosols thrown into the air.
Yeah.
But they are not always red color. They might be coated with sulfur, nitrate, and so on.
Yes.
Show you the dimming effect instead of the.
Well, it depends on the background environment. Okay. See, that's why I only show the maritime type of or amphibian type when it's pristine. You know? So that effect will cause the small droplet and cause more longer lifetime of the clouds. Okay. But then the other one, to me, also sent from the continental type.
They are not always the red carbon. It's actually always coated with sulfate nitrate.
Yeah, that's the real word, yes. Yeah, but now even your composite effect could be still dark, in a sense.
Last year, we saw 2 papers published in Science. They are talking about global widening instead of global dimming. They say from the 1980 to the early 1990, that's 3 years, the global dimming due to the increasing loading of aerosols. That 2 papers published last year, they, from their analysis of several ground-based stations over East Asia, many stations where they found actually there's a quite global widening.
Yeah. This is what I'm saying. We invite the controversial discussion because that after 真理越辩越白嘛。We should get more in this understanding. Yeah, it could be you don't see part of the picture. One part you look at it is dimming, the other part you put it widening. Okay. So, but if you put a bigger picture, look at together, it depends on which way you're coming in.
That's very interesting. I think the effect of mass loading and tropical cyclogenesis is now on the frontiers of earth science research. We are very lucky to Professor Tsai to come here today to show us the frontiers and what they have been very hard work doing on this new study. My final question, does IBM sue you for the deep blue?
IBM? No.
Yeah.
That's computer, no?
Right. So,
if they sue me, I'll go to the jail because deep blue is coming for me. I name it, I name it deep blue, but
Right. Oh yes, Elisa, final question.
Indian region, it is transferring only the central part of India.
Yeah, the dust storm coming from the top or from Arabian Peninsula. Yeah, during the pre-monsoon season, Indian monsoon like May or June at that time. Yes, it's a lot of dust here. That's always come out of the elevator heat pump still. But we saw that the dust coming in and then going through this Indo-Gangetic heavy polluted or heavy particulate. It produced a lot of soot because India burning a lot of biofuel, coal, and fossil fuel. So that produced a lot of soot. We saw it, yes. Actually, I have another picture that I didn't show. Space shuttle, we look at that, the Indo-Gangetic. It's really cold, round cloud, and really soot. Yeah. But that's why I'm really like, I spent a lot of time in India and talking to the young scientists. Actually, we need that part of the participation. The young scientists have to participate.
We have one event in Woolly Mountain. We may detect sometimes burning from India on a Thar desert.
Really?
Last year, 2 years ago.
Really?
Possibly, without.
There's another experiment called Indo-X.
Indo-X is a long time ago, 1999. Yeah. So after Indo-X was the ABC. Yeah, I have a lot of history. Do you want to ask about it? There's many politics in between.
Right. I think we heard many very inspirational aspect of this new observation and the new evidence that will give us many to think about within a weekend.
But old men.
Yeah, at what? So.
Excellent result.